So, hello everyone, this is Jean-François Filipot speaking from France Énergie Marine. I'm pleased to open the CTech Week session, which is named Waves and Wind Observation for Offshore Renewable Energies. So first of all, I would like to thank the organizer of the CTech Week to have offered us the opportunity to hold this host this session. And I'd like also to thank the speaker from DTU, Charlotte Hasager, Helmholtz-Zentrum Geesthacht, Jochen Horstmann, Pedro Guimaraes from France Énergie Marine, Alexis Mérigaud from IFPEN Énergie Nouvelle, and Florent Guinot for Naval Energy for the time they spent preparing the slides and for the time they spent preparing the conference in general and registering and so on. So I would just make a quick introduction with a few words about the context of the session, and I will be quick because you will see the same kind of arguments in the different talks. So the rationale is, so first I would like just to define what is offshore renewable energies. So by this we mean offshore wind, fixed and floating offshore wind turbines, tidal turbines, wave energy converters, and ocean thermal energy conversions. So today we will mostly speak about offshore winds with the different speaker we have. So why wind and waves information matters when it comes to the deployment of offshore wind turbines? So first, the most obvious reason is that we need to estimate the resource to know how much power we can get from the wind and the waves. Second, we need to know what are the standard conditions at the sites in terms of wind and waves to know what will be the fatigue of the turbines, what will be the extreme waves and wind faced by the structure to make sure that they will resist the most severe storms they will face during their lifetime. Of course, we should be able also to forecast wind and waves for operation and maintenance. Also for farm operation to make sure we extract the most of the energy available. And so as you noticed, the title of the session deals with observations. So why do we need observation? Why can't we just trust numerical models? So there are a few points that you can see here. The first point is that the models are usually validated using single point measurements. And we don't know much about their ability to represent the spatial variability of wind and waves. And there was new sensors that allows us to do that now. Second point is they are not always suitable to represent extreme wind and waves. First of all, because the data, the observations that are required to validate the model in this condition are quite rare and difficult to collect. And also because these conditions involve different processes, nonlinear processes that are sometimes not accounted for or poorly accounted for in the numerical models. And the last point that I listed is that if you want to get a fine description of the wind turbulence at a site, if you want to be able to access a very short time forecast to collect information on gust or wave by wave, if you want to deploy or if you want to board on a wind turbine, this kind of information is not accessible by numerical models. So this is basically a list of what we will discuss today. And now I will leave Florent Guinot from Naval Energy. And sorry, just after that, I would like to discuss the session content. So after my talk, Florent Guinot will discuss the key methodology information required for the design of floating offshore wind turbine from the point of view of a substructure floater developers for floating wind turbine. Then Pedro Guimaraes will tell us how we can collect sea surface images to resolve space-time wave field that could be useful for the design of the wind turbine, for instance. Jochen Horstmann from Germany, SZG, will tell us about his expertise and experience using marine X-band radar for wind and wind gust measurement at offshore wind farms. Then Charlotte Hasager from DTU Denmark will will explain us how we can measure winds from space for offshore wind application. And the last speaker will be Alexis Mérigaud from IFPEN, will present us some results dealing with the real-time forecasting of ocean waves and ship motions using a stochastic approach. And then we'll have a 15 minutes question-answer interactive session. So now I'm pleased to introduce Florent Guinot from Naval Energy, who will share his screen right now and tell us about his point of view regarding what is required to design the floating offshore wind turbines. Florent, can you try to share your screen now?
Thank you, Jean-François. He's just telling me that I cannot share while someone else is sharing.
Okay, let me try to unshare mine then, or okay.
It's fine. It's just the time for
okay, transition.
Transition, yes. Can you see my screen? Perfect. So good afternoon, everybody. So I'm Florent Guinot from Naval Energies. So I'm leading the site characterization and mooring department of Naval Energies. I will present you briefly what the company is doing and what we do with the meta-ocean information that the other speakers try to gather as accurately as possible for our needs. So let's start with a quick company presentation. It won't be long, and afterwards I will just show some examples of data analysis and data statistical work we used to do in our daily works. So what are our missions? So basically Naval Energy is, the mission is to design, manufacture, deploy and maintain different solutions for marine renewable energies. So we are mainly active now in floating offshore wind and in deep sea conversion, OTEC, thermal energy that Jean-François already mentioned. So for floating wind, we are working mainly on the floater. We are not dealing with the turbines. So we are developing floater and the anchoring system and all the operation and maintenance of the systems. So just a quick historic view of our short life. So we started, let's say about slightly more than 10 years ago as a department of ex-DCNS, which is now Naval Group, who wanted to develop their expertise in terms of marine renewable energies. So then they focused on floating offshore wind around 2009. And thermal energy in 2010. And the main project we had recently is the Groix-Belle-Île project in the French, in the south of Brittany in France, which is composed of three, it's a pilot project composed of three turbines, about 10 megawatt each, which are going to be installed in 2023. So we started this project about 7 years ago. About 4 years ago, sorry. And just another topic we have worked on recently is, and maybe you have heard about it, is this data center which has been submerged by Microsoft in Scotland. So we have been deeply involved in it, in the conception of the vessel and in the installation and recovery, because it has been recovered this year. So it's a data center which has been submerged during 2 years to see how the equipment behaved in the water compared to the similar equipment in a classical data center. And then you can see different partnerships we had with the Japanese companies, and I won't go with the different commercial prospects we have, but just to give you a quick overview of our past experiences. Just one word that Jean-François already mentioned, the market behind floating wind. So we are talking of thousands of gigawatts of potential worldwide, mainly in the US and Europe. and Japan. So our proposition is to provide floating foundation and the mooring system, the full OPCI solution, and the solution for the industrialization and local manufacturing. So this was just a global overview of the company and regarding floating offshore wind. Now I will just focus on what my team does. So what do we do in terms of site characterization? So we have a multidisciplinary team working on oceanography, geomatics, geosciences. I will be quick to go deep into the details afterwards. So basically the main topic is the metocean characterization. So we're talking of wind, wave, current. We're working quite a lot on seabed characterization, mainly for the mooring foundations. A lot on design load cases definition. I will talk about it in the next 2 slides. So how do we synthesize all the information we have in terms of design load cases? We carry out spatial analysis and layout optimization, so mainly for the mooring systems and to optimize the positioning of all the equipments after looking at the seabed characteristics. We work on the accessibility studies to estimate the weather windows for installation, transportation, and maintenance. And then 2 other topics that were slightly less doing at the moment because it's mainly the work of developers, project developers. It's environmental impact assessment that we have carried out before a few years ago, and natural hazard estimation, so like tsunamis, earthquakes, or cyclonic events. So this was a quick overview of what the company is doing. And now we just go, I think, in 4 slides on different specific topics that we have, issues that we have, and how do we work with the metocean data. So as an introduction to this, you can see here some requirements that we used to get from developers or turbine manufacturers, and some operations which are greatly influenced by metocean conditions. So of course, this is non-exhaustive. So we have plenty of parameters to look at. So the angle of the machine under nominal thrust and in extreme conditions, nacelle acceleration, tower-based bending moment, offsets, the mooring line tension, extreme and cyclic, and all the effort in the structure as well. And then when we talk about operations, we have to study metocean data to assess the best period for nacelle assembly, the possible weather standby we have. And it's the same for transport and installation and accessibility during the operating life of the machine. So we have plenty of different topics with plenty of different metocean data required at different levels of accuracy and with different parameters which are required. So just the usual process to obtain relevant metocean information. So it's obvious for most of the people around the table, but basically what we do is we carry out in situ measurements over a limited period. So you can see here current profiler and LiDAR, onshore LiDAR. The aim of these measurements is to get a reference information and to have complementary information that numerical model cannot provide. The second step is to, based on these measurements, is to run numerical simulation to get information over a long period, which are required for the fatigue analysis and extreme analysis. So this simulation have to be calibrated and validated with these measurements. And then afterwards, we have plenty of statistical data analysis to answer to all the different topics I just mentioned before. So this is quite classical process. Ideally, we would like to work only with measurements, which can be better to provide information, but sadly, it means that we would like to have 20 years of measurements, which is not feasible for different projects. So we have to go through this process of measurement, simulation, and then analysis. So then I will just highlight 4 examples of data analysis that we do in our work. So let's have a look at fatigue analysis. So if we want to size accurately the systems and subsystems, we have to characterize precisely the constraints And the objective is to reduce the risks and to optimize the cost. So basically what we get as a basis is the years of meteocean information. So here you can see some wave and wind information. But of course, we cannot run these 20 years of information in our model. So we have to make synthesis of these environmental conditions in a limited number of design load cases. So basically, the idea is to simplify these 20 years in, let's say, 100 cases, representative cases for preliminary phases, up to 2, 3, 4, 5,000 cases for advanced studies. So that this exercise of a combination of lots of parameters to have a limited number of environmental load cases, which represent the whole life of the system. So we have developed internal multivariate analysis tool. I won't go into details, but it's just to highlight that something which is really important to us is to have cross correlation of all these parameters, so that we make, because usually we used to have a combination of one parameter versus another one. But in our case, it's not sufficient because we have to combine lots of parameters together. And so we have this process of design load cases optimization, like let's say to optimize some groups of environmental cases together with significant parameters, and then if we combine these hundreds of thousands of design load cases, we expect to represent fairly accurately the whole fatigue life of the system. That was just first example. Then we can talk about the extreme. For the extreme, the problem is a bit the opposite, is that compared to fatigue, where the time series is a bit, let's say, too long to be handled by engineers. For extreme analysis, the time series is too short because we would like to see what would be the condition with a storm with a 50 years return period or 500 years return period. So now the issue is the opposite. So we have to extrapolate and get more information based on a limited data set. So I think everybody is kind of familiar with the univariate extreme analysis. So based on one parameter, it's quite straightforward to make this kind of estimation. Based on 20 years of data, you can extrapolate what would look like the 50-year storms or 500 storms. But it's not sufficient for us because we cannot work only with one parameter. We have to deal with all the parameters we can characterize the waves or the wind. And so the main issue for us is to have joint extreme analysis. So here you have two examples of extreme analysis regarding direction, if you look on the left. Our extreme analysis based on two parameters. So here you have peak period and significant wave height. So it's some types of extreme analysis which are quite common in the domain, but then we have to look at the combination of wave, wind, and current together to see what would be an extreme event, because we cannot sum up the 50 years wave, the 50 year wind, the 50 years current. It would be too harsh for us, so we have to make a clever combination of this. And then we have all the other parameters which characterize these events. For example, for the wind, of course, we can easily get the extreme wind, but then what would be the extreme shear, the extreme turbulence? And for the waves, we have plenty of associated parameters such as the peak, the spectral shape, the directional spreading, and it's all this information that we need to make an accurate design. Just another issue, the accessibility studies. So here it's not, when we are talking about the project, we're mainly looking at one single point where the machine will be installed. But if we take the example of our project, for example, in the south of Brittany, it will be the nacelle assembly will happen normally in Brest, and then the machine will be towed around Brittany up to the final installation site. So we need to have refined information of wave, wind, current along the route and at the harbor for nacelle assembly. And so we need to have special information that could be provided by satellite. Or right now, we are mainly using numerical information, in-cast data. But we need to have not only information at the site, but at all the different places where the system will pass by. And then on the right, it's just an example of how we can estimate weather windows and operation duration of a, let's say, what we call a complex operation. A complex operation is just that we have different place in space and different operation in time with different restrictions. For example, for the nacelle assembly, we'll have some restriction in wind, then some wave restriction for the towing, then some wave restriction for the hookup. Everything has to be carried out sequentially, and then that's what we aim to mean, sorry, by complex operation. Just last example, and then I will conclude because I think I'm not watching time, but I won't be too long. So just an example of information. Usually when we talk of waves and wind, we mainly talk about significant wave height, peak period, and mean velocity. But for us, the spectral shape and the individual wave height and gusts are really important. Here you can see an example of wave and wind spectral information and how you clearly see the same shape for the tension in one mooring line. So it's just to highlight that global parameters is not sufficient for us. We really need to go further in terms of spectral shape and gust, for example, for the wind. So I mainly it was just to introduce some topics we have. So basically, we are talking of key methodology information, but so for the wind, we are used to work with mean velocity and direction, but we need a lot of other information. Let's say, for example, the vertical shear, the turbulence, the spectral shape, as I mentioned. For the wave, it's the same. So we have the directional spreading, the spectral shape, the C-state partitioning, the individual wave height. For current, of course, we usually get mean velocity and direction, but we also need vertical profiles, the separation of the different phenomena, such as tidal, atmospherics, internal waves. And then we also have water levels that I didn't mention before, but it's quite important for us. And so for all of these parameters, we need the normal and extreme condition. And the main point for us is that we need the relation between all these phenomena, because we cannot deal with each of them separately. We really need to have the clear relation between all these parameters so that we can have proper design load cases definition. That's it. So thanks for your attention. I think the questions are not now, so feel free to keep them and ask me the question later on.
Okay, thank you very much, Florent. Yes, you're right. We will have the question session at the end after all the talks. So now we are moving to the talks from Pedro Guimaraes from France Énergie Marine. Pedro, can you please share your screen?
Can you see my screen and hear me? Can you just...
Yes, go ahead, Pedro.
Okay. So thank you all for having me here at the CUTEC Week conference. I'm Pedro Guimaraes. Here is my email in case you would like to contact me. So today I will present you about sea surface stereo video image to resolve the space and time wave field, not just a single point, but space and time resolution of the surface. And the work that I will present here, it's a joint collaborative work between France Énergie Marine and many other collaborators and many other authors. So I would like to thank you all for their contribution, and also include Farivalise from Brest that helped us to make this this experiment possible. So in the context of the new demand, the new world energetic demand, we have more specifically the green energetic demand for our planet. The wind turbines can present a huge potential to supply that demand. because the wind can blow almost interrupted offshore and provide more stable conditions for imply wind turbines than inland. However, floating wind turbines create a new challenge for renewable energy designs because they can be exposed to storms and heavy winds and heavy weights that can jeopardize the turbine structure. So it's fundamental to have a better knowledge of the meta-ocean conditions in order to build a good design and more efficient designs. More specifically, the waves. When the waves break over the platform, we can have very heavy loads over the platform structure that can jeopardize it, and that is not just the movements created by the waves, but also the impact created by wave breaking the platform that can be very important for planning marine operations or planning the design of the structure. So with that in context in mind, we develop the DIME project. That one of the objectives that goes it's to increase the knowledge of extreme sea states for marine renewable energy system, MRI. Science include extreme wave breaking in that sea states. Provide accurate breaking statistic from waves models, improve waves models resulting in storm conditions using more accurate breaking parameterization, optimize MRI machine design for providing more realistic storm condition information, and develop a standard methodology to observe extreme waves conditions, including the distributed load over offshore wind turbines. So to do that, we develop an experiment at Largemont Lighthouse. This is a historical lighthouse in northwest of France. And we choose this place because it's the bathymetry goes very fast from zero, where it sits the rock platform of the lighthouse, to 80 meters depth, very, very, very fast. So here is a picture of the lighthouse during a very calm condition, but we actually choose this lighthouse because it's very exposed to extreme conditions. So here it's just a video of the lighthouse during a storm condition, and I would like to take a moment just to watch a little bit this video, because there is I think it's very beautiful, the waves breaking over the lighthouse and how this lighthouse is hanging there for more than 100 years. It's a very beautiful engineer structure and design problem. So this location of the lighthouse, it was chose as I told, because it's very often exposed to storm events. In 2014, at the Pierre Noirbuy, that it's very close to Largemont Lighthouse, it was measured maybe one of the biggest waves in France of 24.2 meters from crest to trough, not HS. And also in the same day, we have 3 successive waves that were recorded with wave heights over 17 meters. So this is a very energetic place. So it makes a great place to study extreme conditions. And according to Prévost, this particular region in France, we have a very short return period of storms. So for the waves that has a return period of more than 100 years in most of the coast of France, that are waves over 11.8 meters. At Largemont Lighthouse, we have a return period of only 10 years. So I think we have the experiment hanging there for for less than 10 years, we probably can get very big storms and measure very huge waves and very huge HS. So this is a bathymetry plot of the experiment that we have at the Largemont Lighthouse with some equipment. So in the lighthouse, we have a X-band radar that was installed in the top of the lighthouse that covers this circle area. I hope you can see my mouse moving. So you have this circle area in the plot in the left that it's the area covered by the X-band radar. The orange area is the area of the stereo video records. And this pink line, it's an area that we have more or less some coverture between we expect some coverture between the radar and the stereo video. We also have a data well buoy that a bit offshore from the lighthouse, and we used to have a walk in the bottom, very close to the lighthouse and inside of the stereo video. But this walk was destroyed after the passage of the first storm that was found in the island nearby. We managed to recover the SIM card, but the record was showing like very heavy movements of the equipment with more than 45 degrees. So the data was basically useless. But I'm saying that just to show that traditional oceanography methods to measure the extreme events, they are very rare, or maybe they don't get good measurements of the surface elevation and what really is going on in the surface. So this is why stereo video, we choose stereo video to do that measurements. So here is the stereo video system. The stereo video system is basically two cameras, two video cameras, very well synchronized, installed in the top of the lighthouse, that enable us to reconstruct the wave field. We also had installed in the lighthouse a pressure sensor to measure the impact of the wave over the structure, and a few accelerometers that were installed inside of the lighthouse at that positions, and I'll talk a little bit about it later. So for us that are not familiar with stereo video yet, the system is just based in two synchronized video cameras, so camera 1 and camera 2. And when you have a pixel position in the image of camera 1, and you find the same position of the pixel in the camera 2, you can apply just a geometric, and you can reconstruct the CS surface. Speaking quickly, is that so? It's like it's like a wave. It's like you have a range of many wave buoys. Like each pixel of the image acts as a wave buoy for you, and you can have like a surface elevation map in space and time. So for the first experiment that we did in Largemont Lighthouse, we recorded several big storms. These ones are the biggest storm that we recorded, from HS over 10 meters for 2 records of HS over 10 meters. And we have some lot of measurements with HS over 7 meters. But one of very interesting event kept our attention. From the accelerometer data, we noticed a significant horizontal acceleration in one case, and that was very peaky. And if we compare to all of the other hackers, we still have some peaks in the horizontal acceleration data, but this one was a lot bigger than most of the other events. So when we look the stereo video data for this case, we had this huge wave breaking in front of the lighthouse and actually over the lighthouse structure. And that creates like a big splash in front of the cameras that float the cameras that are at 47 meters high. So what these particular waves has different from other waves is from all of the other waves, they broke, the crest broke lower than 14 meters high. And why 14 meters high is important? Because 14 meters high, it's the elevation of the base of the lighthouse after the reinforcement. The lighthouse used to be lower than that, and then they reinforced the structure until 40 meters. And that wave particularly break higher than that structure and hits directly the lighthouse wall, creating a huge vibration because this part is not so reinforced as the base of the lighthouse, and then give us that acceleration signal in the lighthouse structure. So here just a different representation of that. It's a record of the stereo video, but just in 2D. This is measured 50 meters away from the lighthouse, so it's not actually over the lighthouse, and I just put the lighthouse in perspective so we can have like some idea how big was that wave that hit the lighthouse if we compare with the size of the lighthouse. So the wave is coming, and then you can see that overcomes the barrier, the 14 meters barrier. This is 50 meters away from the lighthouse and hit the lighthouse wall. And this is a picture get from Emmanuel Denier and Nicolas Fadi for the same wave that in a study that is published at Philosophical Transaction A 2019. And they also actually measure as well more or less the same results, and they estimate that the wave height and the breaking point, it was about 18 meters, and 14 meters was the structure of the lighthouse. So this is the same picture. I just would like to show that we are looking at the synchronization, and if you look the time of the picture, that it's storage inside of the camera, that was taken from Oasen Island with very good zoom lens. And if we look the image from our cameras at the same time, this is what's happening. So good match. So just a summary and of what we have done so far and some perspectives. Largemont Lighthouse revealed to be a very good location to study extreme waves and the effect on the offshore structures. In the winters of 2017 to 2018 and 2018-2019, we observed some giant waves with some waves larger than 24 meters. And we also observe very large extreme breaking events that hits the Largemont Lighthouse. So in summary, Largemont could have a second-like service as a reuscated laboratory condition to study extreme waves events and also their effect on offshore structured law. With these experiments, we're hoping to create a measurement protocol that's able to investigate the 4D properties of the surface elevation and breaking during extreme events, and also how they should affect the tower and other wind turbines or offshore facilities. In a continuation of that, now we have the DIMPACT program, and we are planning to install the same system in a real wind turbine very soon. And if you are interested in this study, most of the results that are presented here, they are published at this paper at Philosophic Transaction A. And if you are more interested in the data of the stereo video, all the data that I showed for the extreme wave breaking in front of the lighthouse and flooding the camera, that data is fully available for people from the publication that we did in the scientific data. With these and other breaking events and other surface elevation records from stereo video, we published not just the stereo video outputs, but also the image, the raw image. All the codes are available, and also all the configuration files are available, so you can reproduce it by yourself and try to get the same results as we got for this experiment and many other experiments. So thank you all, and I think the questions will be later, and that's it.
Okay, thank you very much, Pedro. So the next speaker is Jochen Horstmann from HZG in Germany. So please, Jochen, could you share your screen?
Yeah, thank you, Jeff. I will be talking about the marine radar, and in particular with respect to wind and wave measurements, and just for also in the concept of using for offshore wind farms, but you of course can use it also on moving platforms or at the shore. The marine radar was in general designed to actually measure nautical parameters, distance to land, other ships, etc. And we are more or less misusing it. We are using the noise of that radar to retrieve other parameters. The nice thing about the marine radar is it's a fairly cheap instrument. It is used on more or less all vessels, and you can use it on vessels at shore-based stations, or like here on the right-hand side out of offshore platforms like this Guinot 3 tower. So it's also, I think, an ideal instrument to install on wind platforms. It's operating at X-band. You get it at different powers. The power is more or less gives you a farther range. We are operating typically as favorable instrument, the 12 kilowatt, which is not much power for marine radar. You can operate with different antennas, which give you different resolution and azimuth, meaning the radial component. You can also operate it with different polarizations, where we are in favor of vertical polarization, just that you have an idea. Typically, ships use horizontal polarization, but you can also do all of this I'm showing here with horizontal polarization. The radars typically you buy off the shelf are incoherent. We have made our radar coherent. Coherent means that in addition to measuring the intensity, you measure something like Doppler speeds, which gives you additional information I will come to. The resolution and range is typically for these radars just 7.5 meters, which is the main problem of the radar to our knowledge, in particular when you look at waves. If you're looking at winds, it doesn't really matter much. And the resolution in azimuth, as I said, is dependent on the size of the antenna. If you have these biggest 12 feet antenna, you have a resolution of up to 0.6 degrees. You can operate them remotely, but you can also operate them directly on the platform. And most of the parameters we're retrieving, we're trying to get in near real time, which is not always possible. In general, you can get a lot of different parameters from the marine radar. I have put a list here together. You can get all kinds of different wave parameters, starting with the integral parameters, the spectral parameters. You can learn something about wave breaking. We're working on getting individual waves. We have shown that you can get excellent surface currents from the marine radar and the quality similar to the ADCP. I will show you that you can get some wind parameters. We have shown that you can also get bathymetry with not really excellent quality, but you get some indication on what's going on in shallow water. And it's really often used for surface features, which are, for instance, internal waves which show up in the marine radar or others. But I will focus here on the wave and wind parameters. So in general, the first idea was, why do we actually do these wind measurements? Yeah, everyone is measuring winds, but with the marine radar, you have the chance of measuring the wind not at the platform, but actually in a certain distance. So you have no real influence of the structure itself. So the first idea was, how do we get better wind measurements from vessels? But of course, this is also applicable to wind farms, etc. So here as an example, we just plotted two reference sensors from a vessel, which are mounted in slightly different heights, but in particular different positions of the vessel. And you see in general, the correlation looks quite nice, but there are some big outliers which are actually due to the influence of the vessel. And that was something we thought we can actually get rid of by using marine radars, as we're not looking near to the ship, but in a certain distance where nothing is influenced by the vessel itself. For that, we had the luck to be able to participate as the Ocean Naval Research Experiment High-Res in 2010, where we actually had a radar on a vessel on a mega tower. So that's not the usual position you have a marine radar, but in this experiment, we had the luck that it was up there. And on the so-called flip, also really up there. So we had no influence of vessels like shadowing, etc. And we used these measurements to compare to the wind measurements taken at this flip tower. So very ideal situations. If we look at the wind retrieval, so we developed a method to retrieve winds from the marine radar. In general, it's dependent on the intensity. We get a mean error of the wind speeds of about 0.4 meters per second, which is, for a good measurement, not really, I mean, on these wind farms, I assume they get better measurements, but on a vessel, you do not get as good measurements. So it's for a remote sensing device, a really nice and fairly high accurate measurement. Nevertheless, there are disadvantages. In case of rain, you have influences, so we do need to throw away some of the data. So it will not work at all conditions. With respect to the wind directions, we get an error of about 8 degrees, which is also quite accurate, at least for the applications we had in mind. When we're looking at wind farms, like what I showed you before was the mean wind speed and direction within an entire image, which has about the size of 3 by 3 kilometers, 6 by 6 kilometers. So if we're looking at a wind farm, it would be really nice that instead of getting the mean, we would want to get a wind field in such a big area. And if we look at these marine radar images, like this is a coastal station at the coast of Italy, where we saw offshore blowing winds, and you clearly see these different patterns. And if we can retrieve actually these patterns in wind speed, that would be a real interesting thing for wind farms. Actually, the idea of doing this came from a wind farmer who saw these images and said, can you give me these wind fields? So we started the project to try to get wind fields. The main idea is actually we take individual images. Every 2 seconds, we have one rotation of the radar. So on the left-hand side, you see every image represents about 2 seconds. If we average these images, we get rid of these weird structures here you see, which are actually due to the winds, so due to the waves. And we have to remove these wave structures to get a proper wind field. We do this over 30 minutes, which is not a real nice wind field, but you will see, will show interesting features. If you take the mean intensity over 30 minutes, you see the dependency of the winds. Actually, you see azimuthal dependence. The wind direction in this case was like shown here by my mouse. So you have a directional dependence, you have a dependence of the intensity on range. And then this feature you see here is actually shadowing due to the position where the radar was mounted on this mast. But in general, we need to have a transfer function getting from this intensity to a wind speed. We managed to get that by machine learning and end up actually with a mean wind field shown here to the right, and here we retrieve every 30 minutes a mean wind speed. So note that the wind speeds are here shown in a range from roughly 9 to 10 meters per second. So you see very small details, and actually these white marks here show wind farmed, individual turbines which do show their wind turbulent wake, just the stuff we saw before in this nice image. So you really see very small scale changes in the wind field if you take a long mean average. For another application, the idea was, okay, what about the wind farms in many places in the North Sea have the problem that they need to be very certain about the amount of energy they bring into the net. So they really want to know if there's a wind gust coming to prevent of getting too high power into the net. So they have to steer that somewhat by all the individual measurements on these wind farms. Now here the idea was, can we give actually some information about wind gusts in the entire area? I will show you here that there is every couple of seconds we're generating actually a mean wind speed map around the radar positioned here. You see it's about 3.2 kilometer range, covers a huge area. And we compare these measurements we're getting from the marine radar. We always compare the mean in all these different 5 windows. These are the color lines here. And we're comparing this. Our measurements are 10-meter winds. We're comparing this to the measurement on the mast at a height of 80 and 106 meters. And now I will play this video and you will see how a gust is showing up here in the corner. And you will see how these measurements slowly peak up and come to the wind farm with the delay as measured here at the location of the wind farm itself. So the idea here is, can we actually give a 30 to 60 second prediction of a wind gust coming, and also about the area which is covered by this wind gust? Our first results show we can, but the accuracy is not very accurate. So our main issue here is actually to propagate this wind field. The measurement of the wind field is okay, but the propagation of this gust is fairly complex and difficult. So we have to put in a little bit of more effort to get that better predicted. The same radar and the same data, and that's the nice thing, you do not have to change anything. You can take the same data set and you can actually measure the waves. We saw these waves here, like in the intensity image, but we're also looking at the wave information, like here on the right-hand side, in the Doppler information, where you clearly see the scattering facets going towards, this is the wind direction in this case, towards the radar and then away from the radar. And the idea is here, what kind of wave parameters can we get from this data? Of course, it's easy now to see the wave directions. You can see also the wave periods and distances, but we have to also get additional information like the significant wave height. The method we have been using for many, many years now is actually what we call spectral filtering, where we look for the energy of the waves in the so-called wave number frequency domain. That way we can get rid of a lot of noise we have in the images and come down to a much better noise-free spectra, wave spectra from this imagery. So from that we get nice information on the peak wave directions, peak wavelengths, peak periods. But the thing which is really now still missing is the so-called significant wave information, which for most of the things is the main interest. In addition, we also get from the dispersion relation, which is shifted due to the currents, we actually get from this dispersion relation filtering the currents. And actually we get the currents with an extremely high resolution, and in particular with a really, really small error of about 4 centimeters per second. However, we're measuring the surface currents, so in the upper 3 meters. With respect to the significant wave height, is the really difficult parameter to measure. Many years we tried to get the significant wave heights from the signal to noise ratio, and nowadays we have shifted to looking at actually Doppler speeds, where there are a lot of contributions which are included in the Doppler, but one important contribution is the so-called orbital velocities of the waves. And we use this physical approach to actually get the significant wave height. And we have shown that if we only use the physics-based approach, we get a root mean square error of about 20 centimeters. If we do a little bit additional calibration, so with additional calibration constant, we can reduce this. However, in that case, you need buoy data. So this approach, fully physics-based approach, should be good enough. It will not replace a wave rider. A wave rider is more accurate. However, positioning of a wave rider is expensive and difficult, while a radar is significantly cheaper. However, we think the main advantage of using radars, and this is a little bit of ongoing work. We have started this in a project recently, but it's ongoing work. We're trying to retrieve individual waves from the marine radar. Just as we have heard before from the stereo camera images, we try to do the same from the radar images. Here you see a representation of intensity images which were converted into a wave field. And you do see that there's some regions. We have the shadowed area here where we actually have bad information. These were the shadows due to this mast. But in addition, we see that cross wave directions. This also doesn't look like a real wave field. But mainly we are interested actually in the waves approaching us. So we would be looking more into another area in front of the radar. The same we can do for the Doppler. By the Doppler, we're using in this case the orbital velocities to retrieve the individual waves. So at the moment, we're still working on an approach where we combine both information, but I will only show you how to use the Doppler information, because the Doppler information is at the moment the better information we are getting. Again, we have the shadowed area. We have again the cross wave issues here. However, if we look upwind in this area and use this area actually for short-term prediction, I can show you first results. All this is preliminary because our main problem here is how can we actually validate these individual waves? So we need measurements of the individual waves outside in this area. And look, this is a quite big region of about 2.5 by 2.5 kilometers. If we take now these data and try to do an individual wave prediction of about 30 seconds, and we compare the results here at this blue point, then this is what the comparison shows. We have typically root mean square error of the individual waves of about 50 centimeters. But note in this case, we have a significant wave height we had of about 3 meters. So the error is within like 15%. If you measure from, it's a significant wave height of 5 meters. We measure here the distances from trough to trout, but also here we're looking along a line here and not in the vicinity of this point, which would be the better way to compare actually trough to trout. Another thing we're doing here, and why we believe the error is still a little bit bigger than we would wish it to be, is that we're comparing here at the same time stamp, meaning we believe that we do not do any phase errors. A small error in the phase of the waves will of course lead to additional errors. So we believe even there we can show that this is a very useful tool for predicting waves, big waves coming up to maybe a vessel or a wind farm when people are going over to the wind farm. The same we did for a 60-second. With 60 seconds, the errors go significantly up. And we believe we can do a good job with linear wave theory by only 30 seconds. With 60 seconds, we need to consider a lot of more additional information to get something useful out of it. But as I said, this is an ongoing project, so we have another 2 years left to solve this problem, and we believe this is a real nice tool for a short-term wave prediction. If you have these individual waves within your image, you can actually do something like what was done with this Straubner wave. You can investigate, in addition to the individual waves, you can actually look at wave groups which are in particular problem or could get a problem for vessels or also floating wave platform, offshore wind platforms. So by just looking for the envelope, you could investigate these wave groups. And actually, if you do that with a marine radar image, you can do this in space and time. Here, this is just using our marine radar products, but where I already said, forget about these cross wave stuff. We're taking the entire image, assuming these are the true waves, searching for the envelope in two-dimensional area, and can observe them actually in space and time. And this is in deep water and shallow water. So things do obey here the linear wave dispersion. If we look at this now with respect to intensity, so what are the biggest wave groups? And that's, I think, more of interest for platforms as well as ships, etc. Then we can actually search for the peaks. And with the peaks, we can actually also search for their propagation in space and time and learn a lot about how these wave groups in reality behave. I mean, we know how they behave theoretically, but here we can actually look at this in real wave measurements. Of course, we're not at this stage, we're not at the point yet that we can say the individual waves we're retrieving from the marine radar are really true, but we do have very much hope that they are really not bad, and we need to now compare. That's why we want to compare to stereo cameras, but we also need to compare in a region farther away. So we need wave riders, AWACS, etc., to get a better idea of how well actually, how small or big our errors are and how to improve things. So in general, that's how I want to close. We have some kind of a nice method to get wind fields with accuracy, which still has to be validated. However, the propagation of these wind gusts, etc., we can show, yes, these agree in time, etc., but we still have to improve the forecasting. That is some kind of a modeling effort. We have shown that we get excellent significant wave heights and spectral parameters from marine radars, and we're working on these individual wave things. We do get results. We still have to validate so that we have an idea how accurate are actually our individual waves. We have shown that we can actually use the marine radar for short-term forecasting of extreme events. And we have shown that there are nice methods as soon as we know the accuracy of the marine radar wave fields, we can actually nicely observe wave groups, individual waves, and energy distribution of waves in space and time. So for questions, we wait for the last talks, and I hope you have now an impression what you can actually do with marine radars. Thanks.
Okay, thank you very much, Jochen, for this nice talk. Just I would like to invite the audience to ask questions through the chat or the tools that they have through the interface, because we are still waiting for questions right now. So please feel free to ask questions while the speakers are speaking, so that we can prepare the question session in advance. Thank you. So next speaker is Charlotte Hasager from DTU. Charlotte, could you please share your screen now? Charlotte, I can see your screen, but I cannot hear you. Maybe you're mute.
Okay. Now I'm unmuted. So, yes, thank you so much for the invitation to present today. And for anyone who wonder where I'm coming from, I'm from the Technical University of Denmark, the Wind Energy Department. And I'll talk about measuring winds from space for offshore wind energy application. So there'll just be a brief introduction, I think actually summarized by several other speakers. And then I'd like to focus on cluster effects and wind resources, and a very few words about wind LiDAR. Well, just brief about DTU Wind Energy. We have 250 employees, all involved in wind energy research. Yes. Well, wind energy in Europe is producing a lot of electricity, and this graph shows how much production on average one has, and a country has per year. And as you see, EU 28 has about 15%. Offshore is a little part. Denmark has 48% wind in our electricity system, and quite a large part from offshore. And then other countries have also quite some offshore wind. And there's a vision for much more wind in Europe offshore. We have currently 22 gigawatt installed, and some are predicting we could have 450 gigawatt by just 30 years from now. Well, to produce power, you need the air density, the area of the rotor, and the wind speed to the third power. So obviously, the larger the turbine, the more production at a given site. And these large machines are what we are testing at DTU Wind Energy. They are installed at our test sites. Here's just a vision from a few years ago, but it's always busy, fully booked with larger and larger machines. Well, the wind farm wakes, as I already saw Jochen as well, showing this beautiful picture where there's some fog. I wrote this article about the fog, why it comes and what it means for the production. And funny enough, in this case, most of the turbines are not in operation. It's just those in the front line, and the last ones are passive because the wind is very, very low. In this case, 4 meters per second. But what happens when wind's going into a wind turbine is you have a wind profile, the turbine pulls out energy, and after that you have a little less speed behind it, and you also have more turbulence. And this is what we see in another photo of this. It's 8 years later, and the neighboring wind farm. And we then investigated from the scatter data with Ørsted, how much is the production, and can we model this production? And the arrows to the left shows the production from every turbine, and you can hardly see there are two arrows. So well do they fit the model and the observation. In this case, we have high winds like 10, 11 meters per second, meaning you have very long wakes, very narrow, and every turbine is in operation, except 2 for service. We also modeled the entire wind farm and the cluster effects to a second wind farm. And this is really my topic, why I'm presenting it, is to understand that from one wind farm, the combination of the turbines add into a wind farm wake. So here we come in with the offshore from satellites, the wind maps from synthetic aperture radar, where we mainly use them for wind resources to understand the gradients in wind speed near the coastlines, where people usually plan their wind farms, then the wind farm wake effects, and then the model validation. So below you see this type. I'll come to detail with each of them. And we are basically using Envisat Sentinel-1, A and B, and they are radars. What we do is we download this continuously directly and processed to wind maps. If you go into this website free of charge, you just register with a mail, you can download, well, access 276,000 wind maps from across the world. And based on this information, we're looking into things about offshore wind energy. Here we see a map of some wind farms, and I will zoom in on the red square, where we see several wind farms. And the SAR image to the left is from CLS, and it's actually a RadarSat image. But what you see in this raw image is dark shadows behind the wind farms. The wind is from northeast. And then to the right-hand side, you see that we are also modeling these wakes. And we find that they are of similar size and direction for the cases. Here is another case. It's just two wind farms in the Belgian waters. And this model is running every 30 minutes to present the velocity deficit relative to a free stream. And you see that these wakes are extending very far away from the wind farms. So the next I would like to present is the wind resources. Well, last year we released the Global Wind Atlas 3.0, which covers, as you see, all land and a coastal zone around 100 kilometers, or a bit more somewhere. Within this, in the scientific part of it, you also can access the resource maps from satellites, both SAR and ASCAP. But what I would like to show here is that for every time you are modeling, or we are modeling, or somebody is modeling the winds for the resource assessment, it is interesting to investigate how does the SAR images map the winds at the same time. And here we have the Harmony model run by Icelandic Met Office and the SAR images. And when you're going into sort of details on atmospheric flow patterns, we see at the top that the model is really able to capture the lee effects. On the lower hand, or the below, it looks like the Harmony model is, say, under-predicting how much wind is coming from land and offshore. But it depends on the features, the type of atmospheric flow phenomena, whether the models actually capture it or not, or only partly. So here we have taken the black triangle. This is an ocean in the Danish seas, and the black triangle is a wind farm 20 kilometers long and 5 kilometers wide. And to the left-hand side, we have taken all the SAR images that's Envisat from before the wind farm was constructed. And to the right-hand side, we have the WRF model. So that's the wind resource estimate, same color scales. So next, I'll show you that this is how the wind farm looks. It's like a triangle. And then we have the scatter data from Ørsted, from all the turbines. So we can say the turbine wind speeds are measured. So we have a truth of what is really, when we look at this one, what do we trust the most? The satellite winds or the modeled winds? Here I show the outlay of the wind farm, and I just highlight all the turbines at the rows. And to the right-hand side, we are looking at the row A, meaning the one to the west. And we normalize this wind speed data to make it more visible what it really is. So you could say the truth is the scatter data. That's the blue curve. The WRF model has the black curve, which is a little more smooth. And then we have the SAR winds from the satellite, and that follows the scatter data slightly better than the WRF model. So we can say that the satellite data produces more fine-scale features than the WRF model. We also have had a study, Tobias Aspas. He was visiting the US during his PhD, and they have, this is the US East Coast, 20 areas for offshore wind, designated areas. So what he was doing in his study, he looked at all the SAR wind maps from all of those, and what you see to the right-hand side is the blue ones, and that shows the wind speed in each of those 20 areas with the mean and the maximum. The yellow ones to the right-hand side shows the mean wind speed from an atmospheric model, and that shows the mean wind speed and the mean and the max. The first you will notice, except for one place, is that the mean and max from the model is always smaller than the mean and max from the satellite. And that just means that within that area, the variation in wind speed is truly larger than the models predict. And the second I think you can notice is that when the further south you go, say Delaware, Maryland, Virginia, actually even the mean wind speeds from the WRF model and the SAR do not really correspond. And that means, in this case, that it looks like you are over-predicting from the model the resource at the sites. So it would be wise to go out and make a measurement campaign before investment. Just checking my time. Yes. Yes, so we need to find out what is the wind speed at the hop height of turbines. And this one shows at the x-axis the wind speed, y-axis the height. And satellite winds are observed at 10 meters, the black thick line. Now, if the wind is neutral, stability is neutral, then we could say we have the same air temperature and sea surface temperature. And we have the blue line, which is the normal simple assumption that we have this type of profile. If the sea is warmer than the air, we will have unstable, that's the red. And that means a more vigorous or effective mixing of the winds. And if it's stable, that means colder sea than air. We will have more wind at a higher level. So when we go to hop height and we assume the neutral profile will get one wind speed, while if we really include the stability information before we go up and assess the wind resource there using the satellite data, we can get biases depending on what is the average climate stability at a site. And here we show some results from the Baltic Sea. To the left-hand side, we have taken the 10-meter winds from the satellite and lifted it up or extrapolated it up to 100 meters, just assuming a logarithmic profile. To the right-hand side, we have assumed we have the stability that we have. Yeah, we have it from models, the stability information, but we have then applied it to extrapolate up. And you see then the winds being higher than. There's something called the New European Wind Atlas. And maybe I should actually swap one. The New European Wind Atlas is mainly a model, the WRF model run for the entire domain for 30 years at a 3 kilometer resolution and at several heights, and it's all freely available. Well, to actually compare this model output to something, what we have done is we have taken the entire archive we have, which is basically the entire archive of SAR images, and upper left is the mean wind speeds from this. To the right-hand side, you see how many samples we have, like it's very well mapped near Norway, Denmark, Baltic Sea, a little less in the Mediterranean, but still good enough. And then to the lower left, we have 100-meter winds. And that is without stability This is with the stability correction. And to the right-hand side below, we see the difference that happens if we are assuming a logarithmic neutral profile everywhere. Then that would bias it positively in the Baltic Sea, Black Sea, and along some coastlines, and negatively in some other areas. So this just indicates how important the stability information is. Also, if you measure the winds at a low level and you want them higher up, even you don't use a satellite, you still need to do these corrections. Yeah, I'm just jumping to that one. And then the wind lidar, which we are also working a lot with at the Technical University of Denmark. And those devices are sitting on platforms typically and measure the winds with a laser. And it can look like that. Yeah, there are different types of devices. Okay, I forgot to show, but there are also a lot of them available on floating platforms on buoys, which is good for deeper waters. Or actually, maybe just to avoid all the flow distortion that comes from installing it at such a bulky thing as we see here. So in conclusion, the wind farm wake and cluster effects is possible to observe it with satellite SAR, and we use different models like Fuga and WRF to actually model these flows. Then we have the offshore wind resource. We usually observe it with satellite SAR, and we usually model it with WRF. And just a simple recommendation, I think I would recommend to measure the winds or observe the winds using the SAR, even just to find out where you need to install your lidars, or if you really need it, if you trust the model. And also measure with lidars to get several heights measured. Yeah, so that's, yes, that was my presentation.
Okay, thank you very much, Charlotte. So again, please feel free to ask questions regarding the current talks and the past one. And now we are welcoming the last speaker, which is Alexis Mérigaud from IFPEN. Alexis, would you mind sharing your screen now, please?
Yes. All right. Can you all hear me now?
Yes, thank you. Go ahead.
Okay. Thank you. All right. So, first of all, thank you, Jean-François, for welcoming my talk in spite of the very late notice. So I'm a research engineer at IFPEN. So first, here is a brief overview of today's talk. I will introduce IFPEN very briefly for those of you who may not know who we are. Then an overview of the topic, then the specific approach that we are developing for real-time wave forecasting. And I would like to spend some time on specific application case studies, some of which are quite nicely related to some of your earlier talks. So a couple of figures about IFPEN, which is a French public sector research and training center. Unfortunately, given the current context, some of those figures may look much less favorable in the next couple of years. So here are the main strategic priorities of IFPEN. The project I mainly work for belongs to the new energies part of those priorities. And more specifically, it deals with offshore wind and ocean energies. So those are a couple of examples of projects, industrial projects that are led at IFPEN in this area. The group where I work specifically deals with with wave energy, which is a very new topic, also not quite a mature one, but some of the applications that we are developing can have interesting applications in other areas like offshore wind energies and other marine industries. So now let's introduce the topic itself. So what do we mean by real-time wave forecasting? We mean forecasts of time series of the wave elevation or the wave excitation force or the motion of a ship and so on. And those forecasts have a time horizon that can go up to a couple of minutes into the future, but not much more. They are based on measurements that are updated in real time, so typically every second or every 2 seconds. So this is actually exactly, Jochen showed us an example of this earlier on. So this type of forecast should not be confused with the forecasting of sea states. The applications for wave forecasting can be categorized into 2 types. The first type is control applications, where by using predictive control, you can improve the performance of some control algorithms. So that's primarily the reason why we started looking into this, because wave energy systems require wave predictions in order to derive the maximum amount of power from the waves. There are other applications like decision support systems for diverse offshore operations. I just noted a few of them here. And we also have to state, I think, from the start that real-time wave forecasting is still not a major technology, although a good progress is being made. Now, how do people generally carry out real-time wave forecasts? There are 2 main families of approaches. The first one is the cheap one. It's the time series approach, where you only use the past data of the physical quantity that you are trying to predict. So, for example, if you have a wave buoy, you are going to use the past few tens of seconds of the buoy records to forecast the next couple of seconds. We can show that actually by only using those data, there is only so much that you can do, and you can never exceed prediction horizons longer than a wave period or so, which can be enough for some applications, but which is not enough for a whole range of applications, such as the decision support systems, for example, which would require at least 30 seconds or 1 minute of prediction horizon. The second family of methods is what can be termed distributed approaches, because they use distant measurements of the surrounding wave field. So the example given by Jochen was exactly of this type. So possible sensor candidates can be radars, lidars, stereo cameras, which all have the property that they can measure at a glance the whole wave field around a ship, for example. Then there are various methods regarding how you use that recorded data. So you can either estimate a finite number of wave modes that you further propagate in time and space, or you can use the observed data as a boundary condition to propagate the solution of differential equations, also in space and time. And then the physical model with which you represent the waves can be either linear or non-linear. Of course, the latter option involves way heavier computations. Of course, between time series approaches and distributed approaches, there is a sort of gray zone, because you may say that you can just use a finite number of measurement points at the surface of the ocean, and in that case, you are not really in the distributed scenario, but you are not either in a one-dimensional time series as before. We are working in a slightly different perspective, because we adopt a statistical model for ocean waves. And this approach has the benefit that it can encompass any of the aforementioned categories. So you can either use that in a time series configuration, or by using a large number of measurement points at the ocean surface. So let's go into a bit more detail about this method. I'm going to try to explain it without resorting to any equation. So the assumptions underlying the method are very standard in marine applications. We assume a Gaussian wave field that is stationary and homogeneous. And we also assume that we know the wave spectrum fairly well. The measured data can be either point measurements, as I mentioned earlier, so wave buoys, the data from the ship's IMU, inertial measurement unit, or the motion of a wave energy device in our case. You may also use more distributed measurements like radar data, optical measurements, and so on. You can also combine any of those measurements. And we try to predict typically the motion of a ship, but that can also be a wave force, a wave elevation, or several of those parameters. Now, the mathematics behind the method. So, given the Gaussian assumption that I mentioned earlier, we can consider now that the data that we have are a stationary multivariate random process. And thanks to the knowledge of the wave spectrum, we can determine the covariance between every pair of observed or predicted data. And knowing these correlation values or covariance values, we can determine what the best linear predictor is for what given the measurements available and the quantity that we are trying to predict. So this can be summarized in this small diagram. So from the wave spectrum, you can calculate the covariance matrices between all the data points that you're trying to use. And from those covariance matrices, you can determine two important things. The first one is the optimal prediction matrix, which is going to be used then in real time to carry out the forecast every second. And the prediction error covariance matrix, which tells you how accurate your predictions are going to be for each time horizon. The expected benefits of the method are plentiful. So first of all, it's supposed to be optimal in a mean square error sense. So that means that regardless of the other method that you may try to use, if the other method is using the very same data, it cannot perform better than this. Of course, this is provided that the Gaussianity assumption and stationarity assumptions are verified. The method is also very efficient and simple because the only real-time task to carry out is a matrix multiplication. So it's hard to find anything faster than this. Also, another handy aspect is that it provides a statistical characterization of the prediction uncertainty. And finally, you can combine measurements of various natures, and you can also reconfigure the approach depending on the measurements at hand. So, for example, if you have an obstacle that is blurring some part of the radar line of sight, you can reconfigure the method and find the optimal predictor for the data that remain visible by the radar. So now let's have a look at a few case studies at IFPEN. So the first one is concerned with a wave energy converter prototype developed by SBM Offshore. It's made of a very long tube that is flexible and made of electroactive materials, so that as the wave passes by, the tube inflates and the electroactive material delivers some power. It is crucial to this concept of wave energy device to be able to forecast the deformation of the tube at each sensor location. And so we have been working on this aspect with SBM through a project funded by a French research agency called ADEM, funding agency, sorry. So as I mentioned, the goal is to predict in real time the deformation at each sensor. And so we are looking at two approaches. Both of them we treat using the our statistical approach. So in the first case, we carry out the forecast at each sensor individually. So that's a time series configuration. In the second approach, we use the information from all available sensors to carry out the forecast at every other sensor. This is the experimental setup at École Centrale de Nantes. So this is a long wave flume, and the device is located inside the wave flume. And we look at 4 different sea states. And these are the results that we obtain in terms of correlation for every time horizon at sensor number 50. So this is one that is quite far from the wave maker. And as we can see, so the purple lines indicate the time series case, while the green lines indicate the distributed case using centralized information from other sensors. So we can see that there is very clear benefit in using distributed information, since obviously upwave information will give us a hint of what is going on in the next couple of seconds. Also note that this time horizon of 10 seconds may seem very brief. However, this whole experiment is scaled down. So 10 seconds corresponds to, so for example, in the first wave spectrum, 10 seconds actually correspond to 5 wave period, which is quite a lot, and is actually far beyond what SBM needs for their control application. Another point I wanted to underline here is that, as I mentioned before, the approach gives us the expected forecast accuracy. This is indicated by means of solid lines, and we can compare that to the accuracy obtained in practice, which is the one with dots. You can see that the performance observed in practice is extremely close to the one predicted by the model. Now, another case study is this time, just checking the time, should be fine. This time in a simulation, we wondered what we could possibly achieve if we had a very nice radar available. So we numerically generated a fake radar dataset, very simplified because we assumed that this ideal radar gives us the exact wave elevation value and not some backscatter intensity data. So this is very simplified, but this still can give us an idea of what can be achieved. And we tried our method and compared it to another widespread method, which is let's say the most common that you can find in the literature. And we found that by using only the red circle of data, so only like the very boundary of the observed domain, we can achieve a better performance than the other method, which uses the whole radar snapshot. Here, that's for, so the wave spectrum information is indicated on the left-hand side. This is a short video that shows how that would look like in practice. I hope you can see the video work. So you can see the prediction going on in a receding horizon fashion. So the blue line represents the actual upcoming wave elevation, while the red line represents the prediction. You can see that the red line comes closer and closer to the blue line as we get closer to present time. We can also see that the approach provides a confidence interval that is represented as well. This is very useful to the operator who can know to what extent he should be trusting the forecast. So another case study that we just started to look into comes from a nice stereo data set that was made available by Pedro Guimaraes that gave the talk earlier. I think that Jean-François is also involved in the main publication. And so we first looked at the Korean datasets in this study. There are a couple of challenges associated with this dataset, especially very strong current, very steep waves, and a quite a restricted spatial window for the estimation of wave spectrum. So we started to try to overcome some of these challenges, and here are a couple of examples of measurement configurations and the associated prediction results in terms of correlation. The red line represents the correlation expected from the theory, and the blue line, the one that we obtain in practice. And as you can see, there is still a small mismatch between both, and we are now trying to figure out how to reduce this mismatch. Just to clarify, the blue points in the upper graphs are the observed data points, while the red dot represents the point where we try to forecast the wave elevation. As you can see, by combining the several arcs of data, we can improve the forecast for every time horizon. Here is an example of how the prediction looks like with respect to the actual wave elevation. Here, that's 12 seconds ahead, so two peak wave periods. This looks a little similar to what Jochen was showing earlier on. And that's it, because I think I am running out of time. Thank you.
Okay, thank you very much, Alexis, for this very nice talk. So now it's time for the question session. So it seems that we are having some technical issues, so that the audience might not be able to ask questions. But still, I think we can have a few exchanges regarding the work that has been presented. So I can start with a question for Charlotte. Let me try to open the chat.
Okay, I'm unmuting myself, being ready.
Okay, so yes. So the question is, what model are you using for correcting the wind maps for atmospheric stability?
We are using the WRF model at a fairly high resolution in the studies I have shown, but we are thinking that it could be useful also to use ERA 5 if you don't have a high resolution product, or if you want to do it in a remote place in, say, Asia, and you don't have it. But otherwise, of course, the WRF model at high resolution is what we're using.
Okay. So what are the parameters do you require from the model to correct?
We use friction velocity, air temperature, and the Mononovikov similarity L value, this large L. Yeah, that's the main parameters, and the heat flux, actually.
Okay. Okay, so not directly the sea surface temperature.
No, we don't use this because, yeah. No.
Okay. Okay, thank you. And another question for you, Charlotte, is when you showed your maps with the error of WRF downwind of the turbines, yeah. Is it because the resolution it was not enough, or is it because the wake effect is not well parameterized in the WRF?
Yeah, it's a good question. If we knew, we could solve it. It's difficult because there are different theories on how to make a parameterization for how turbines affect the atmosphere. You know, if you go down to really fine scale, you use a CFD model, an actuator, and all of that. But when you get to larger scale, you need actually to find out some simplified ways. You could say you assume the turbine is like a tree, a forest, like kind of passive, and add some roughness in. But that's also not the full truth. And yeah, so there are basically two working lines these days. One is from the US, from Julie, what's her name? Julie from University of Colorado, and her group. They have the Fitch parameterization, which is probably most used, and they developed it on large land wind farms in the US. And then we have one developed by one of our colleagues, previous colleagues actually, a wake parameterization that was developed offshore for the Hornsrev wind farm in the North Sea. Which one is better where? It's very hard to say.
Okay.
There are two basic choices here.
Okay, okay, thank you, Charlotte. Next question is for Pedro. So what is the accuracy of the stereo wave retrieval method? What are the limitations beside light? And what is the round distance the system can be utilized for?
Well, can you hear me?
Yes.
Okay. It's the stereo video really depends on the system configuration. I think for the case that I showed for Largemont, the expected error, quantization error was about 9 centimeters. And of course, there is a lot more involved. Like one of the limitations, it's sometimes during the breaking, you have too much foam that saturates the image. And in that case, the error can be a bit higher. So it can create some spikes that you need to remove. So yeah, beside the light conditions, the limitations are, I would say, the camera, the lens that you use. But there is a lot in play. But I would say that depending on the lens that you use, you can get better correlation or worse correlation. You also need to check if you put zoom and you get some blur in the image. It's also complicated. A problem that we had a lot in that experiment that makes maybe most of the image unavailable was droplets in the lens. We have a wiper to clean the lens, but we just do not have the wiper in front of the camera. We usually wipe the cameras and clean the lens before starting acquisition and after. And if we have some rain and droplets in front of the camera, sometimes the image was useless. And yeah, and sun glint. Sun glint, it's one of the worst problems that we have to deal. So sometimes during sunrise and sunset, depending of your location, you have some problems with stereo video as well. What was the other question about? Was something about the location, elevation, or something, right?
Range resolution, how far you can look.
Yeah. So it really depends of the cameras. If you are using zoom lens, you can go a lot farther. And if you are using wide angle lens, usually you have a better resolution very close to the cameras and worse resolution far from the cameras. So if I'm not wrong, for the case that I show you at Largemont Lighthouse, we have about 0.5 centimeters, very close to the cameras. And as we are going look farther, you can go to 1 meter different distance between the pixels, and as you go farther, the resolution will decrease. But yeah, I think it was that for Largemont. Does that answer the question?
Your mic is muted, Jeff.
Okay, sorry. Yeah, question for you and now. Thank you, Pedro. So people are thinking of equipping wind turbine with horizontally looking lidars. They are very expensive, and you claim that your radar are very cheap. Do you think that we could use your radar to do the same kind of measurements, or if not, what would be the limitation?
I believe so, because I mean, we have the advantage of looking in space and time. So the time is, I guess, similar resolution as with these horizontal lidars. However, we are looking at the whole spatial domain. The main difference is that the lidars are hub height, so they will be measuring the wind speed at hub height, which is an advantage. We are measuring wind speed at 10-meter height, or more or less we are referring it to 10-meter height. However, if the hub heights are not too high, we can convert also using models to get our wind speeds to the proper hub height. We are using Toga Core 5, which would be good for maybe 50, 60, 70 meters. When it gets higher, I'm not sure if you can use such a simple approach. So we're measuring different things. However, we're measuring the spatial domain, so also the size of the radar. So I would think so, yes, that is a solution, but it would have to be checked. It depends a little bit on what you really need.
Okay. And so you showed this very nice animation of the wind speed blowing offshore. And I was wondering whether you have some limitation measuring the wind very close to the shore. Is there like some distance at which you cannot access to the wind speed because there is no ripples or the signal is not good enough?
For us, the limitation is minimum wind speed. So typically our measurements start at 2-3 meters per second. Below that, the ripple waves we need to see are not generated. That's one limitation. So that is not really a limitation to the distance to shore because these waves happen after a very short distance to the shore. And then we have a further limitation is that the farther away we want to retrieve the wind, the higher the wind speeds have to be. We have a range dependency, so we will not get enough backscatter very light winds in a far distance. So the stronger the winds are, the farther we can look. However, we have thresholds, so we know when we get a good estimate and when we do not get a good estimate. So we can do some kind of error analyze.
Okay, good, thanks. So question for Alexis maybe now. Alexis, your work is based on Gaussian field theory.
Yes.
Obviously, you are missing all the nonlinear patterns of the waves. Do you plan to work on that with a physical approach or machine learning approach to capture these nonlinearities in your model?
So we already have like sort of quick fix for that worked very well in some cases. So for example, SBM gave us simulation data from a highly nonlinear model of their system. And this worked pretty well. Actually, the experimental data with their system did include some level of nonlinearity already. But for the future, as Jochen said, if you are using very distant data, then probably nonlinear interactions are something that you may have to take into account. So we are now planning to first carry out work to quantify how much nonlinearities affect your predictions. And if so, how we are going to deal with that. So we have several ideas, but we'll probably have someone doing a PhD with us to try to work on these aspects. Probably a first step would be to take into account some nonlinear dispersion relations. But for now, we cannot be sure that this will be enough.
Okay, thank you very much. Okay, so it's about time to close the session. So I would like to thank you again, all the speakers for their time and the very interesting talks that definitely give us some ideas where to go in terms of R&D dealing with site characterization, wind and waves observation in particular. It's a very difficult exercise because we don't know who is connecting and how much people are looking. So just for the speaker, I didn't communicate on that, but there was 71 people that registered to our sessions, and it is in the best scores when we compare to the other sessions. We will have the number of people involved in the session later. I will let you know. And I would like to invite you and the audience to visit the CTech Week conference that is online, and also to contribute to the B2B meetings. This is a message from the CTech Week organizer that I have to pass over. So it's 6 p.m. And again, thank you for your time, your effort, and I hope that the audience enjoyed the talks. And hopefully we will have another session like this for the next CTech Week. Thank you all. Bye-bye.